For decades, the physical reality of engineering was defined by vast rooms of drafters performing manual geometric calculations by hand. They relied on physical tools, compasses, protractors, and mechanical arms, to translate complex mathematics onto paper. The flaw in this system was the physical medium itself. A line drawn half a millimeter off scale compounded as it moved across a schematic, resulting in massive structural misalignment at the job site. At the scale of mid-century infrastructure projects, the margin for error was razor thin. A physical drafting mistake could risk physical collapse. In December 1982, AutoCAD shifted the drafting medium from the physical pencil to a computational data structure. By digitizing the process, spatial reality was stored as mathematically perfect data, targeting the elimination of the physical margin of error. Take a look at this modern commercial building blueprint. Structural steel, electrical wiring, and HVAC routing are flattened into one view, creating a dense, overlapping grid. It looks like graphic noise, but the software organizes this geometry as a structured relational database. This presents a complex logistical challenge for disparate teams. Engineers and architects must simultaneously design overlapping systems without their physical components interfering with one another. To understand how they avoid collisions on the construction site, we have to deconstruct this file. We need to look at the exact data structures and modular workflows that guarantee design accuracy. The utility of this software relies on its ability to manage these chaotic data hierarchies. This diagram isolates a single structural joint on a vector grid. Floating data tags represent mathematical constraints, like line lengths and fixed angles. As a parameter updates from 90 to 45 degrees, the drawn lines instantly snap to the new geometry. This rigid mathematical baseline is stored in a specific container, the DWG file format. DWG is AutoCAD's native repository. It stores both the visual geometric vectors and all the numerical metadata dictating how those vectors behave. When engineers share this data across competing software applications, they use a universal format called DXF. It translates the numerical constraints so other programs can read the file without corrupting the geometry. Large-scale, multidisciplinary projects depend on these standardized formats. Without them acting as a baseline, cross-platform calculation errors would cause complex designs to fail during the transition between teams. Moving up from a single joint, let's examine a repetitive, complex component within the layout, like an industrial HVAC unit. Instead of drawing hundreds of lines, engineers use dynamic blocks. This HVAC unit is a pre-packaged cluster of geometry. Altering the parameters of one unit forces an automatic update across the entire project file. Change the shape here, and every identical block morphs to match. This modularity shifts the engineer's focus toward high-level systems layout rather than repetitive drafting. To maintain order between these blocks, the software uses parametric constraints, rules dictating how different design elements must relate to one another. For example, if a structural wall is moved, the parametric rules ensure the attached plumbing geometry travels with it automatically. These interconnected tools act as a defense mechanism against revision errors. A design pivot that once required weeks of manual redrawing can now be executed in seconds. Zooming back out to the separated building systems reveals a major logistical hurdle. A single user manages this complexity using internal layers. This visual filtering system allows an architect to toggle the structural steel off while keeping the electrical data visible. Internal layers organize a single file, but modern projects require coordinating different files across separate engineering firms. To solve this coordination problem, the software utilizes external references, or XREFs. An architect's master file passively links to external working files. Distinct structural, electrical, and HVAC overlays merge via glowing XREF data links. These update live. When a partner team saves a change remotely, the master layout instantly shifts to reflect the new data. This live synchronization prevents physical interference. It ensures that an HVAC duct isn't accidentally routed through a steel I-beam. By transforming isolated drafting tasks into a synchronized master plan, XVACs function as the operational backbone of modern construction. Eventually, the digital abstraction has to translate into physical execution. The data model must guide the heavy machinery on the ground. To bridge this gap, the software compiles its database into standardized, printable construction documents using sheet sets. These organized documents directly inform exact quantity estimation, material resource planning, and the overall project budget. Today, cloud collaboration delivers this data securely to the field. The job site foreman accesses the same model version on a tablet that the offshore engineering firm sees on their desktop. This cloud integration closes the loop between design and execution. Aligning the physical build with the digital truth avoids millions of dollars in potential rework. Over 40 years, the core logic of AutoCAD has moved toward a fully parametric, multi-layered relational database. This database is also spatial. Here, we see the multi-layered 2D architectural logic smoothly rotating along an axis and extruding upward, forming a solid, readable 3D model. This 3D extrusion provides the foundation for Building Information Modeling, or BIM. BIM integrates deep real-world metadata. It allows engineers to simulate gravity, lighting conditions, and thermal dynamics in software long before breaking ground. The technological frontier builds on this concept with digital twins, a live, real-time reflection of a physical building's performance, rooted in the initial CAD model. AI-assisted drafting utilizes these established mathematical constraints as the parameters for generative design. By automating thousands of structural iterations within those limits, the software can find the most material-efficient and sustainable solutions. Mastering CAD software requires commanding the spatial data engines that design, simulate, and optimize the built environment.